Hi, in this video we're going to talk about the mean value theorem and a couple of other related theorems, and then also do an example. Okay, so the first thing we're going to do here is look at the statement of the mean value theorem and be sure we understand everything it is saying. So I've written this theorem here on the page so that it's clear what the hypothesis and the conclusion of the theorem are. So when you think about any theorem, you need to make sure that the hypotheses are satisfied, and if they are not satisfied, then the theorem doesn't apply to whatever function you might be looking at. All right, so this theorem has two important hypotheses. First of all, our function has to be continuous on some closed and bounded interval, a to b, and the function also has to be differentiable on the interior of that interval. It can also be differentiable at the endpoints, perhaps, but it's only required to be differentiable on the inside of that interval. All right, and if both those things are true, then we can draw the conclusion that's here after the then part of this statement. So it says there's at least one x value, so that's important that we might have more than one. X equals c in our interval a to b, that open interval, such that, and then a couple of important things about this statement. So there's something about a derivative on the left side. Be sure that you are paying attention to that derivative notation on the left side. But on both sides of that equation are things about slopes. All right, so on the right side here, what we've actually got is the slope of the secant line between the endpoints. And then the other side of the equation, f prime of c, is the slope of a tangent line at some x coordinate x equals c that's in between a and b. So this is about slope of a tangent line being equal to slope of a secant line and at different points. All right, so let's look at some pictures down here below so that we're clear about what that's saying. So I've just drawn some examples of two different functions, and I want you to just focus on the picture here, not worrying about the equation. We will look at an example where we look at the equation. All right, so both of these show functions that are clearly continuous. There are no breaks in the graph between two endpoints. So this one has an endpoint at x equals -1 and another endpoint at x equals 4. And so that function is clearly continuous on the interval -1 to 4, no breaks in the graph. And also thinking about slopes of tangent lines, it appears that the slope of a tangent line would exist everywhere, or that function is differentiable everywhere between -1 and 4. And so mean value theorem says that there should be a point between x equals -1 and x equals 4 where the slope of the tangent line is equal to the slope of the secant line. So I'm just going to draw that secant line right there. And what I'm looking for is a place between -1 and 4, maybe more than one place, where I've got a tangent line that has the same slope as the line I drew right there. So you're just thinking about parallel lines, but something that's tangent to the curve. So I just visually estimated here two lines that appear to be parallel, so they have the same slope. And I've got that secant line that I started with, and so that point at which that line is tangent to the curve would be our x equals c. And so visually I can estimate that here to be at approximately 1.5. And so I've got slope of tangent line equals slope of secant line at least one point between x equals -1 and 4. All right, let's look at the next graph here. So on this next graph, I've got x coordinates labeled at -2 and at 4. And I can look at a secant line between those 2 points. And again, our function is continuous on the closed interval and differentiable on the open interval between those points. At least it appears to be so from the graph, unless there's hidden behavior we can't see from the graph. And what that theorem says is that there should be at least one point between -2 and 4 where the slope of the tangent line is equal to the slope of the secant line. So I'm thinking about parallel lines that would be tangent to the curve. So there appears to be one right here just past that lowest point, that local minimum on the graph there, somewhere between 2 and 3. So again here, parallel lines that have the same slope. So there would be an x equals c there, maybe at about 2.6 or so. But there are actually a couple more on this graph. So maybe pause the video and see if you can think about where those other points would be, and then restart the video and check. Okay, so other places where I would have tangent lines with the same slope would be just a little bit left of the local maximum that's there, and just a little bit right of the local minimum that is on the left side of the origin there. So also at another point here at C equals approximately negative 0.5 or 6, and here maybe at C is approximately maybe 0.7 or 8. So this is one where I've got really 3 values of C. That theorem says that there's going to be at least 1, but there could be more values of C. All right, so a couple of related theorems to talk about, and then we will look at an example where we have the function equation. So Rolle's theorem is essentially mean value theorem, but with the f of b is equal to the f of a. So the slope of that secant line is 0. So it's saying that if my f of b is also equal to f of a, then there would be at least one point x equals c in there where the slope is 0. So we won't emphasize Rolle's theorem. I do want you to be able to write down mean value theorem. You could know or not know that Rolle's theorem is a special case of that, but mean value theorem will be the one we focus on. And then the last thing that I have on here are that we have 2 other theorems that we've actually already talked about, intermediate value theorem and extreme value theorem. And all 3 of these theorems, the one we just talked about, mean value theorem, and then these other 2 have some similar phrasing. And so I just want to contrast them a little bit to make sure that you're clear about all 3. I really expect you to be able to write down all 3 of them. All right, so I'm just going to kind of summarize here: intermediate value theorem, extreme value theorem, and then the new one that we just talked about today. I'll write some stuff over here. All right, so these are all kinds of value theorems. All of these theorems have hypotheses. The intermediate value theorem and extreme value theorem just require that the function f is continuous on some closed and bounded interval. Mean value theorem, of course, requires that as well. But mean value theorem is also about slope. So mean value theorem also requires that the function f is differentiable on the open interval. The other 2 only require continuity on the closed interval. All right, and then intermediate value theorem is the one that's about the chicken crossing the road, was kind of the mnemonic way that we thought about that. So what it says is that if you have a function and 2 endpoints where the function is continuous on that closed interval, and you think about the output values at those 2 endpoints, and you pick any y value that is between those 2 outputs, so pick any y value that's between them, and we call that y value y naught, then there has to be at least one point where the function crosses that y value. Right, so in this picture I drew, there are actually 3 of them where that function has to cross that y value. So I'm going to write that down in symbol notation. So this is really just about the function having to cross through any y value. Extreme value theorem was what we just did in 4.1, so also this week in what we're working on. And this says that if f is continuous on a closed and bounded interval, then the function f has both an absolute maximum and an absolute minimum on that interval. And it can occur at the endpoints, or it can occur at critical points in the interior of that interval. All right, mean value theorem is the one that is about slopes. The others are really about y coordinates, so highest y coordinate, lowest y coordinate, or crossing y coordinates. Mean value theorem is the one that's about slopes, and so that's the one that requires differentiability. All right, and so I'll just write the conclusion down here, which you actually have at the top of the page here, but I just want to emphasize that that is about slopes. Okay, so all 3 of these theorems are theorems you should be able to write down completely, or answer concept questions, or fill in the blanks for certain pieces of those theorems. So please work on making sure that you can write down all 3 of those theorems. being clear about which ones have different conditions or requirements, and then what is the conclusion for each of those. All right, let's look at an example where we are using a function equation. Okay, so the directions say to determine whether or not the mean value theorem applies to the function on the interval, and if so, to find the values of c guaranteed by the theorem. So two things to check. I need to make sure that the function is continuous on the interval. And if I want to just answer that, I would say yes. But if I want to justify why, there's kind of different levels that you might do that. F of x is a polynomial. And we have a polynomial substitution shortcut theorem that was really about continuity, even though we didn't talk about continuity until after that. So substitution shortcut theorem for polynomials says that the limit as x approaches a of f of x is equal to f of a, and that's the definition of continuity. So that function, because it's a polynomial, is continuous everywhere, which includes our interval that we're interested in here. Okay, so you wouldn't necessarily have to write out all of that to justify why the function is continuous on that closed interval, but at least some of that, or you should be able to recognize a correct explanation. All right, the other condition that I need to check is that f is differentiable on the open interval. It is. One way to justify that is to actually find the derivative. We know some shortcut rules here, so f prime of x is negative 2x plus 2, and that is defined for all values of x, which includes the open interval 0 to 3. Okay, so both of those conditions are met, so mean value theorem does apply to this function. And then I want to find the values of c that are guaranteed by the theorem. All right, so slope of tangent line is equal to slope of secant line. Is how I think about this, and so I'm going to go ahead and write those two things down here. So slope of tangent line is equal to slope of secant line, f of b minus f of a over b minus a, and my a and b are 0 and 3. Okay, so slope of tangent line, that's our derivative, negative 2x plus 2. And then f of b minus f of a, I'm just going to make a little value chart here for function inputs and outputs. So when I put in 0 to our original function, f of x, I get f of 0 is negative 1. And when I put in 3 into the original function, I'll get negative 9 plus 6 minus 1, so negative 4. So f of 3 minus f of 0, so negative 4 minus negative 1 over 3 minus 0. So that's my f of 3 minus f of 0 over 3 minus 0. And now I'm just going to solve for x. I do want to be sure that my x value ends up in my interval. I could sometimes end up with more than one value of x. I would just throw out any that are not in the interval. And I could end up with more than one value of x that actually is in the interval. All right, so from here it's just some algebra. All right, so I got x equals 3/2. That is in my open interval, 0 to 3. So that's my value of c. Okay, you can see here that I have pulled up Desmos, and I went ahead and typed in some stuff here. So I typed in the function that we were working with, and I have a point a, f of a with a slider, and you can slide that around. So our endpoint was at x equals 0, so I'm going to put that slider back at 0. And then another endpoint at b, f of b, and so again you can slide that around. Ours was at b equals 3, so I'm going to put that back at 3. So there is our secant line between 0 and 3. And so this is the graph of the function, just to make sure that the answer we got makes sense. So we got x equals 3/2, so 1.5. So visually, if you look at this, you should see that if I think about slope of tangent line at 1.5, that slope of that tangent line should be the same as the slope of this secant line. I'm going to go ahead and put the tangent line on this graph. All right, so what I have here is a slider down here, and I can drag this around to change the value of c. And so from our calculations, we got c equals 1.5. So let me just drag that to c equals 1.5. And yeah, it does appear that that tangent line is parallel to the secant line. And that appears to be the only point in that interval. So I wouldn't need to look at the graph here, but that's just to verify that what I got from my calculations actually makes sense and that I didn't do something like make a sign error and get the wrong answer. All right, so look at some more examples in those next videos.